So according to Wikipedia, Newton's law of cooling states that the rate of heat loss of a body is directly proportional to the difference in the temperatures between the body and its surroundings, provided the temperature difference is small and the nature of the radiating surface remains the same. Okay, so let's make sense of this law by expressing it as an equation. So it mentions the rate of heat loss here, but we're really concerned with temperatures. So for the most part, a decrease in temperature goes hand in hand with the heat loss. So we let capital T equal the temperature of the body. We'll let little t equal time. So the rate of temperature loss is going to be dt, d big T on d little t, and it's proportional to the difference in temperatures between the body. Now we'll let T subscript S or T sub S equal the temperature of the surroundings. So the rate is proportional to the body's temperature minus the surroundings temperature. And so we can express this as an equation, which means that d big T on dt is equal to a constant of proportionality by the difference in the temperatures. Okay, so let's call this equation 1, which is Newton's law of cooling stated as an equation. Okay, so the article in Wikipedia is a little bit vague on what the temperature difference should be for this law to hold true, but it does say that it largely holds true for convective heat transfer, which is what this equation represents. So let's assume it's true for our problem, which is, let me draw it out. So we have a box here. Let's pretend that it's a refrigerator. So let me draw the power cord. So this is a refrigerator, and let's assume that it's switched on. And we've put a bottle of water. We've put a bottle of water inside of this refrigerator. Okay, so let's pretend that this rather crudely drawn dashed shape here is a bottle of water. It's dashed because it's showing that it's inside of the refrigerator. So inside the fridge, the temperature is kept at 3 degrees centigrade or 3 degrees Celsius. Initially, this bottle of water is 25 degrees. So it's 25 degrees at room temperature when we put it in the fridge. So big T at time 0 equals 25 degrees. After half an hour, let's consider time as in minutes. So after 30 minutes or half an hour, the bottle is at 15 degrees. So we're going to use Newton's law of cooling to determine A, what is the temperature after 1 hour? That's the temperature of the water, of course. And B, how long does it take to get to 4 degrees centigrade? Okay, so let's have a go at this problem. Now what I'm going to do is make a change of variable for this problem. So I'm going to let the function y is a function of t, and I'm going to set that equal to, so we let y of t equal big T minus t sub s, and that means then if we take the derivative of y with respect to time, we should also get d big T on dt. Ts being constant differentiates to 0, and that simplifies our equation a little bit to dy on dt equals ky. And that's simply just by substituting these terms into equation 1. So having done that, we have to rejig our initial condition a little bit. So we know that at time equals 0, y of 0 will equal the water at time equals 0 when we put it in the fridge, minus Ts, and that's simply equal to T sub 0 minus T sub S, which equals 25 degrees Celsius minus 3 degrees Celsius. I'll leave off the units, and that's just going to be equal to 22. Now actually let's put the units in, so it's 22 degrees. So the change of variable just simplifies things a little bit for me. So from here we can go ahead and separate the variables. So we have dy on y equals k dt, and once we have separated the variables, we can integrate both sides. And the left hand side integrates to log of y. The right hand side is kt plus c. And from our previous videos on first order differential equations, which I'll link in the top right hand corner here, we know that the solution y is equal to y0 by e to the kt, where y0 is equal to y at time equals 0, y of 0. So that implies then that y of t is equal to 22 e to the kt. Alright, now we will back substitute the expression for y. So we'll bring this expression down here, because y of t is equal to t of t minus ts, which equals 22 by e to the kt, and therefore big T of little t is equal to Ts plus 22 by e to the kt. Okay, before we solve our questions, we need to find out what the constant k is. Now, because we're cooling, I'm expecting k to be a negative number. But we're given that at time equals half an hour, so at 30 minutes, I'll sub the numbers in. Ts is equal to 3 plus 22 e to the k by 30, that it is equal to 15 degrees centigrade. So it has dropped 10 degrees in half an hour, and that means 22 e to the 30k is equal to 12. So we'll keep on rearranging to find k, to isolate k on its own. Okay, take the log of both sides. If we apply the log rule, 30k we can bring down to the front. So it's 30k by log e, and that's equal to log of 12 on 22. And of course the log of e cancels. They cancel each other out. So the above reduces to k is equal to negative 0.606 divided by 30, which equals negative 0.02. Okay, so this is correct. K should be negative. So our full expression for the temperature at any given time is now equal to T of T is equal to Ts plus 22 e to the negative 0.02 by T, where T is time in minutes. So question A asks what the temperature of the water will be at 1 hour, so when T equals 60 minutes. Okay, so working through that, we have 3 plus 22 by e to the negative 0.02 by 60. And this works out to be 3 plus 6.5, which equals 9.5. So it's about 9.5 degrees centigrade after 60 minutes. Part B asks us, what is the time when the temperature finally reaches 4 degrees? So we want 4 equals 3 plus 22 by e to the power of negative 0.02 by t, and we want to solve for little t. So this becomes 22 e to the negative 0.02t equals 1, which becomes e to the negative 0.02t equals 1 on 22. Take the log of both sides and we'll end up with negative 0.02t equals log of 1 on 22, which equals negative 3.09. So therefore, the time is approximately equal to 155 minutes, and that's roughly equal to 2 hours and 35 minutes. Okay, before I pack up, we can visualize the result, and I'll just do a rough sketch. So let's let the vertical axis be the temperature. We'll let the horizontal axis be the time. We have an asymptote at 3 degrees. We are starting at 25 degrees, and over time we are eventually going to asymptote towards this 3-degree line. It's a bit rough, but you get the idea. Okay, so that'll do it for this video on differential equations. We'll look at population growth in our next video. If you found this useful, please give me a like, subscribe, share it with your friends on social media, and make this channel more popular. If you have any questions, ask them in the comments below. Best of luck with your math studies, and I'll see you on the next video.